Okay, this is a video to review several exam questions for our Mechanics of Energy Systems Exam 1 here for Fall 2020 semester at JCC. I'm doing this because a couple of you have requested it. So right off the bat, I did check that in HD you can read these questions quite clearly that are behind me. If you need to, make sure you put your video settings into 1080p HD. Also, I'm going to try to go quickly so that I don't get cut off by taking too much time up filming. However, remember that this is a video and you can pause. Okay, the first question here. What is the temperature in degrees Celsius at which a thermometer in degrees Fahrenheit reads exactly 1/4 the value of the 1 in degrees Celsius? So I'm going to set up this problem like a simple conversion problem. We have that degrees Celsius is equal to degrees Fahrenheit minus 32 all multiplied by 5/9. Now I'm going to rewrite this, but dropping in for degrees Fahrenheit 1/4 times degrees Celsius. Now I'm going to distribute this 5/9 and I get 5/36 degrees Celsius minus 160/9. I'm going to do two things here. Move this to this side and move this to this side. So I get 160/9 equals negative 31/36 degrees Celsius. Here I've moved over and combined like terms, the coefficients on my own unknown. Finally, I'm going to solve for degrees Celsius by cross multiplying, and I get that it equals negative 36 times 160 over 9 times 31. Do that on a calculator and see that this comes out to negative 20.645 degrees Celsius. Moving on, a vacuum gauge reads 27 kilopascals. The atmospheric pressure is 1 atmosphere. In both kilopascals and psi, what are the gauge and absolute pressures? So first, I'm given a vacuum pressure in kilopascals. So that's one of the answers that I want. Remember that vacuum is negative gauge pressure. So for gauge, our answer right off the bat is that it's negative 27 kilopascals. And then off here to the side, I'm going to convert it into PSI. The conversion factor, which will be on your handout, is that we have about 0.145 PSI per 1 kilopascal. Multiplying that, we get 3.915 PSI. So I can come back here to my answer and realize that a vacuum pressure of 3.915 is equal to a gauge pressure of negative 3.915 PSI. Now I want absolute also. Remember that my atmospheric pressure, absolute, I'll write that over here, 1 atmosphere, equals about 101 kilopascals. I'm rounding up to the nearest kilopascal. All right? So 101 kilopascals minus 27 kilopascals gives me an absolute pressure of 74. I actually left the decimal. This is 101.325. Forgive me, that was not rounded up. That's the exact value. And so the exact value here, when I subtract, comes out to 74.325 kilopascals. And for my PSI, I'm going to remember that 1 atmosphere is about 14.7. It's not exactly, but that approximation is what I can remember. So that will be sufficient on the exam. And to get my absolute, I'm going to subtract the 3.915 from the 14.7, giving me 10.785 PSI. Follow along and check these numbers on your calculator. Moving along. A tomato requires at least 2 megapascals of pressure to be cut. To slice a tomato by applying a 10 Newton force with a knife with an 8 centimeter long blade, what is the widest that the blade can be? Express your answer in micrometers. So I want to remember my formula for pressure. Pressure equals force divided by area. In this case, I'm not dealing with area, but I'm dealing with 2 dimensions that make up area. So I would like to break that down into those 2 dimensions. Length times width. Multiplying them is of course equivalent to area. I'm being asked about the width, so I need to solve this expression for width. What I'm going to do is multiply the width by both sides to bring it up, and divide by the pressure on both sides to bring that down. Simply rearranging, I get width equals force divided by length times pressure. Be sure to check that. I'm going to plug in some numbers. My force is 2 megapascals, or 2 million pascals, divided by a length of 8 centimeters, or 0.08 meters. I apologize, I have put the pressure on the top. My 2 million pascals of pressure, I'll write the unit, that needs to go on the bottom, all right? Note that correction. The top, of course, is the force, which was 10 newtons. This is all in SI units. So I know that when I get an answer out, it's going to be in meters. Okay? So, multiplying these, I'll first write my answer up here that I get in meters. Be sure to check that on a calculator. But we would like to express our answer in micrometers. Micro, from your chart that you have access to, means 10 to the minus 6 meters. So I'm going to bump this over 6 places. Moving it over 6 places, I get this is equal to 62.5 micrometers. Pause now to check anything on this board. Next, water with a volume of 21.5 meters cubed per kilogram is at 30 degrees Celsius. What is its quality? Well, this is a problem that we remember from the lookup tables, but before we go to the lookup tables, we can write down the formula for quality. Quality X equals our specific volume. We usually write average. This is the specific volume that we have, the one given to us, minus specific volume of the fluid. That's all over VFG. That's the formula we're going to use. So if you have your books where we will be getting the lookup tables for the exam, the first thing that we want to check is page 980. This is not going to be where we find our answer, but imagine that you went to this page first because you're dealing with water. If you were to go to page 980 and find it, you would be tipped off by two things telling you that this is the wrong page. Number one, right below the title, the table designation, the title of it is superheated water. And you would remember that for superheated water, there's no such thing as quality. Quality is only in the mixed region where the water is saturated. The second thing that would tip you off is that if you tried to find the specific volume on this page or the next page, page 981, and you scanned through looking for this specific volume, you would not find the correct specific volume matching up with 30 degrees Celsius. All right, so you could conclude that you're in the wrong spot. Now, we'll turn to the right spot, which is where hopefully most of you would turn first anyways, which is page 976. These are the temperature tables for saturated water, which is where we can deal with quality. And we will simply look down the left-hand column until we find a temperature in degrees Celsius of 30 degrees. We will check that if we follow that row across, our specific volume of 21.5 falls within the range given. So it is between 0.001 and 32.879. I'm going to write down those values. VF is 0.001, I'll truncate it there, and VG is 32.879. The first step here is we want VFG, which is simply VG minus VF. To get at, I'm going to subtract this from this. Notice that all it does is change the last decimal place, dropping it down one value. This is such a small number, it's barely any change. Then I'm going to plug in my numbers to this formula. 21.5 minus 0.001 divided by 32.878. Do that on a calculator and check that you get 0.654. I'm rounding to the third decimal place. Okay. Next question. What does this tell us about the percentage of water that is liquid versus vapor? Remember that quality means that we are in a specific volume that is in the region between the saturated liquid line and the saturated vapor line. We've progressed across that region 65.4% of the way. That tells me that 65.4% is liquid. Sorry. 65.4% is vapor, because we're that far toward the vapor side. And the remainder, which is 100% minus this, is 34.6%, which remains liquid. Okay, next, a 190-liter tank contains 400 grams of air at 27 degrees Celsius. The atmospheric pressure is 0.120 megapascals. What is the reading on the pressure gauge? The gas constant of air is 287 joules per kilogram Kelvin. Use the ideal gas law. The first thing I'd like to do is write up here what my units look like in SI. So 400 grams for the mass is equal to 0.4 kilograms. 27 degrees Celsius, the temperature, is equal to 300.15 Kelvin. To get to this, we add 273.15 degrees, the conversion factor, which is found on the conversion sheet you'll be provided with. The 0.12 megapascals, which is the pressure, is equal to 120,000 pascals. The gas constant is given in SI units. And this is atmospheric. I'm going to write down the ideal gas law. P times specific volume equals R times T. I'm going to rewrite it, breaking up the specific volume in terms of big V divided by the mass, which is what it is. And then I'm going to multiply the mass. Actually, I'm also going to divide by the volume. So multiplying the mass to bring it up and dividing both sides by the volume to bring it down. That allows me to isolate just the pressure. Okay? This is the symbolic form. Now I'm going to solve for the pressure by plugging in numbers. 287 multiplied by 300.15 multiplied by 0.4 Oh, I need to add my volume to this list. 190 liters is 0.190 meters cubed. The way that I find that is by taking a conversion factor of 1 meter cubed per 1,000 liters. So now that I've added my volume to the list, I will divide by it down here. And I get out a pressure of 181,354 pascals, rounded to the nearest pascal. Remember that this is my absolute pressure. I would like to know the gauge pressure since they're asking me what is the reading on the pressure gauge. Don't forget this step on your exam. So to find the gauge pressure, I'll mark that as absolute. I need to subtract the atmospheric of 120,000. And I get 61,354 pascals, which is the gauge. And to put it in nice units, I will write it as 61.354 kilopascals. Moving on, refrigerant 134A with a density of 10.2 kilograms per meters cubed has a pressure of 180 kilopascals. What is its temperature in Kelvin? Use a property table. Side note that we did discuss all of the problems in our review last Friday except for this. This is the new one. It will be on the test. So, what we're told is that density equals 10.2 kilograms per meters cubed. We would like to know the specific volume to be able to use a property table. Luckily, the specific volume can simply be found by remembering that it's 1 over the density. So, 1 over 10.2 gives us specific volume of 0.098, rounded to the third decimal place. Meters cubed per kilogram. Now we're going to go to our property tables because it tells us to look up. Just like we did with the previous problem, I want to first take you to the wrong page, page 988. And to reiterate, the reason we're going to the wrong page is to talk through the reason why we don't use that page in case that's where you went during an exam. You'll notice that it is saturated refrigerant 134A. However, it's a temperature table. That means that if you look at the left-hand column, the page is organized by temperature. Okay. We would like our page to be organized by pressure. So, we're going to flip over to the correct table, which is on page 990. It's still refrigerant 134A, this time the pressure table. That's what we're going to use to look up, because in the left-hand column we have pressures. I'm going to scan down until I find the pressure we're given of 180 kilopascals. I'm going to verify that my specific volume is within that range. And so, yes, 0.098 is within the range of 0.0007 to 0.110. And then I'm simply going to read off what the temperature in degrees Celsius is in that row, which is negative 12.73 degrees Celsius. The final step, don't forget this on your exam, is to convert the temperature to Kelvin, which is what's asked for. So, I'm going to again add 273.15 degrees and get a final answer of 260.42 Kelvin. Pause here if you need anything else on this board. Okay. This is our final question. A tank contains 12 pounds mass of air at 40 psi absolute and 70 degrees Fahrenheit. More air is added to the tank until the pressure and temperature rise to 56 psi absolute and 95 degrees Fahrenheit. How much air was added to the tank? Use the ideal gas law. like I did on a previous problem, I would like to start out by converting all of these into absolute units. So our pressures are given in absolute, but our temperatures need conversion. So T1, the starting temperature of 70 degrees Fahrenheit, is going to get converted into 529.67 degrees Rankine, because the Rankine scale is the absolute scale for a problem in imperial units like this. The conversion factor, which you'll be given on your sheet, is you add 459.67 degrees to convert from Fahrenheit to Rankine. T2, the final temperature of 95 degrees Fahrenheit, comes out to this, 554.67 degrees Rankine. All right, I'm going to start by writing down the ideal gas law twice. I'm going to label P, V, and T with a little 1 for the first initial state. And the second time I write it, I'm going to label each variable with a little 2 for the second state, or the final state. I'm going to quickly break this specific volume down into big V over M, like I did before. That's simply giving its definition. Notice that here, I've not labeled this big V with a 1 and a 2. That's because V is the thing that doesn't change about this problem. Of course, since the substance does not change, I've also kept the R without a label. I'm going to take each equation and I'm going to rearrange it, solving for the mass. Actually, what I want to solve for is the thing that is constant. I apologize for that. So I'm going to solve for R divided by V. Or actually, I'll probably do V divided by R. Okay, so here's what I mean. If I take the first one, I get that V over R equals T1 M1 over P1. Pause if you need to see how I got this equation into that equation. Simply multiplying both sides by mass, dividing both sides by R, dividing both sides by P. I get a similar equation with the second one. Just like this. Now, I'm able to set these equal, since this side is the exact same, and say that T1 M1 over P1 is equal to T2 M2 over P2. I'm going to solve this equation to get M2 by itself. I've divided both sides by T2 and multiplied both sides by P2. Now, what I'd like to find is delta M. Delta M is equal to M2 minus M1, and it's the thing that's being asked for in the question. How much air was added? So, I'm going to drop in M2 here, T1 P2 over T2 P1, all times, sorry, I just erased that mistake in this. There was an extra M2 hanging out there, which I did not mean to write. All we have there is the M1. and then minus M1. Finally, all right, this is still to M still. Finally, the last thing I want to do to get a closed formula is factor out an M1 on the outside. So M1 times this factor, T1 P2 over T2 P1 minus 1 comes from taking an M1 out. Now I can plug in numbers here. My mass 1 is 12. My T1 is 529.67. My P2 is 56. My T2 is 554.67. And my P1 is 40. Take a minute to check this calculation, check these numbers, and go ahead and do this calculation. And I got just about 4.04 pounds mass of air that was added. Okay, feel free to pause the video before I stop it, looking at this board, and good luck on your exams.